Hi everybody, this is our video. I wanted to make a little video of 5.4 and 5.5, a few different problems just to show you kind of what's happening. So the first one I'm doing is 5.4 number 6. This is 5.4 number 6. I'm not doing the whole problem, but what I am going to do is do the follow-up pieces. So I've actually filled out the chart here, which pretty much everybody was successful doing. And the idea is the idea was to develop this rule here. The idea was that we could say now the radioactive nitrogen, the amount of radioactive nitrogen at time t was A of t equals 4096 times 1/2 or 0.5 to the t over 7. In other words, every time 7 seconds goes by, if you think about what t over 7 is, it's saying, okay, so if you had t over 7, if t was 7, and you divide by 7, you get 1/2 life. So that means 1/2 is being raised to the first power. In other words, it's being raised to the number of half-lives. If t was 14, 14 divided by 7 is 2. There are 2 half-lives that have gone by, etc. So this function really reveals, the 7 here really reveals the half-life. And you can see that because of the 0.5. The 0.5, this time here, 7 is saying it's going to take 7 seconds for you to reach half of the amount that you had originally. Now, I asked you then to write a model with not t over 7 as the exponent, but t. In other words, I want the model to say, okay, I don't want the half-life. I don't want to be revealing the half-life. I want to reveal the rate per second. In other words, if I think of t as t over 1, whatever goes in here will reveal the rate per second. So how are we going to do that? Well, if I think, there's a few ways to think about it. One way to think about it is to say, okay, I know that A of t is 4096 times 0.5. And if I thought of t over 7 as a multiplying problem, I would think of that as 1 over 7 times t. T over 7 is the same thing as a seventh of t. And then what I can do is I can say, well, this is just as good as having 5 to the 1/7 times t. Sorry, 0.5 to the 1/7. So I then can go to my calculator and type in 0.5 to the, whoops, excuse me, sorry, 0.5 to the 1/7 power. Okay. And then I get 0.90572, which the question asked they said you could round this to the nearest thousandth. So now my model would be 4096 times, I got to get that number back up, 0.9057 to the t. And now it looks more like the models that we've been dealing with. In other words, there's a t here, okay? And so what's happening now is this rate, this is the rate at which the substance, the radioactive nitrogen, remains per 1 second. This is important. Per 1 second, or just per second, because my denominator of my t is a 1, whereas before it was a 7. And so this will actually help us get the percent of radioactive decay. So this is the amount that remains. Remember, this function is telling us how much radioactive nitrogen remains. And so if I think about this, 0.9057 is 90.57%. That's the rate of remain, the rate at which the N16 remains. So if I do 100% minus 90.57%, I get 9.43%, which is the rate of decay per second. So hopefully that makes some sense. And then part E says, find the time t at which there will be exactly 600 milligrams of the radioactive nitrogen 16 left, round to the nearest hundredth. I'm going to use the original model. Actually, it doesn't really matter. We can use either model. So I know that my A of t is 4096 times 0.9057 to the t. This is the amount that's left over. And I want this amount to be equal to 600. So first things first, I'm writing an equation that I'm solving. You would get points for this. You need to write an equation. And we discussed that we currently do not have the algebraic skills to do this. So we're going to do this on the graphing calculator. And so this is a good point to kind of go over windows and things of that nature. So, okay, I go to y equals. I'm going to type in my function 4096 times 0.9057 to the t, or to the x in this case. And y2 is going to be 600. Okay, now most people's windows are on the standard window, which is not going to work for this. And so we're going to have to come up with a better window. And to think about the window, the first thing you need to think about is what is your x and what is your y. X is the amount of time. So if you think about what we did here, we plugged in x for t. So x is the time, and that's measured in seconds. And y is going to be the amount of radioactive nitrogen when we plug in a particular time. This is the amount of N16 left, and this would be in milligrams at any time. So I have to think about what my window should be. So if I think about times, my x's, I go back to my chart, I'm looking at time 0, 7, 14, 21, 49, 84, 72.1. So I'm thinking, okay, I'm going to make my time. I just want to get a kind of breach there. I like to keep the x-min a little bit negative to see the y-axis. And the x-max, I'm going to make it 100. Because I'm looking at my chart and saying, okay, my times are, within 100 seconds or so. Now, my y-max, my y-min, I'm also going to leave at -10. My y-max, well, what was my highest y value? Well, the highest y value was the amount. My highest amount was 4096. I'm looking for 600. So I could make this really as high as 4096. I could make it a little bit lower because I'm looking for 600. I want to make it 2000. Because again, I'm looking for 600, so I can give myself room. And again, you can always go back and change if you don't like it. So here is my exponential curve. It's decreasing. That's good. That's a good sign. Okay. And there is, should be coming soon, there's my line. And I need to find out where they intersect. So I will press second trace 5, first curve enter, second curve enter, and guess I'm going to scroll over to where I think the intersection point is. Press enter, and I get an intersection at 19.39. So then my answer to this would be t is 19.39. And to justify, I need to draw a good graph here. So my graph should show my exponential decay function. My graph should show my line. Okay. I'm going to put this at y equals 600. I'm labeling. This is y equals 4096 times 0.9057 to the t. And I want to show that this is the point 19.39. This is the point 19.39, comma 600, and we have a good graph. And in fact, really should do two other things. This is time on the x-axis and amount of N16 on the y-axis. And now we have a good graph. And you would get points for this, a properly labeled graph. Okay. The next problem I want to tackle is this is 5.5, 1 through 4. So I gave you 3 models, and as you saw in the last problem, the one that we did, we came up with 2 equivalent models. This A of t and this A of t are exactly the same. They're equivalent models. Now, what I showed you in this lesson is that I gave you 3 equivalent models, and I'm asking you to show algebraically how you can transform one into the other. So I'm looking at this as sort of like the basic model that we usually work with. And then I'm looking at this model and saying, I'm wondering if I can translate this model into this one. So I'm going to start with B, and I'm going to say we have A of t is 700 times 2 to the t over 17. And just as we did in the last problem, I'm going to break up this fraction. I'm going to write this as A of t is 700 times 2 to the 1 over 17t. And then we can do 2 to the 1 over 17. And hopefully, this way, the reason why we're doing this is because I have a singular t out here, and this will produce a singular t. So now we can say, okay, let's see what this happens here. A of t is 700 times, well, what is 2 to the 1 over 17? Let's find out. So I'm quitting here. 2 to the 1 over 17 is 1.0416. So this part becomes 1.0416, and I can carry down my t. So now I've shown B is equivalent to A. So we have B and A as equals. Okay. Now, if I'm looking between B and C, I see very few similarities between B and C. So you know what I'm going to do? I'm going to try to compare A to C. Here's A, here's C. All right? And I'll try to show that A and C are equal. And that way they'll all be equal to each other by the transitive property. So, okay. So here's my model in C. A of t is 759 times 1.0416 to the t minus 2. And again, I would like to get this exponent to say t rather than t minus 2. Just like we said, this exponent, instead of saying t minus t over 17, we got it to say t. And I can use laws of exponents to do this. If I think about this for a second, if I think about if I have x to the, if I think about when we're subtracting exponents, when we subtract exponents when we divide. So for example, if I had x to the 9th divided by x to the 2nd, that would be x to the 9 minus 2. So I want to use this in reverse. I want to break this up. And I can do that by doing this. I can do 759 times 1.0416 to the t. And notice how we're using division when we subtract exponents. I'm going to divide by the same base. Notice how my x's are the same. 1.0416 to the 2nd. And think about what this does. What would happen if we were to recombine these is I would have the same base, 1.0416 to the t minus 2. And now I've gotten my 1.0416 to the t. And now it's a matter of trying to get the 759 gone to the 700. But if I look right here, I have 759 divided by 1.0416 squared. And I can do that. I can go to my calculator and I can do that. I can do 759 divided by parentheses 1.0416 squared. Whoops, sorry about that. Square there, delete here, delete that, and enter. And lo and behold, I get 699.58. And for tolerance purposes, this is close. This value is very close to 700. Okay, so this value here is just about 700. So this model is about 700. That part I highlighted in green is now 700 times 1.0416 to the t. And so now we've done it. We've actually shown, we showed that A and B were equal, and we showed that A and C were equal. So we know that they're all equal. Okay, now we're going to try to explain the meaning of 1.0416. So that pops up in our first model. And so we're saying, okay, this is really 700 times 1 plus 0.0416 to the t. And in this case, we have a bank account, okay? So I believe that this is the rate of yearly increase. So this, we can say that the amount of money, the amount of money in the bank increases by 4.16% per year. Per year now, because our denominator of my t is 1. So this is a per year basis. Then we're asked to explain the meaning of 17. Well, 17 came from the second model. And let's take a look. Now if we think about this, my base is not a 1, it's 2. Okay? So let's think about this for a second. What this model is trying to show us is it's trying to show us how the amount of money is going to double. So if I think about what's happening here, if I thought about t being 17, so just bear with me. I have t over 17 let t equal 17 for a minute, then this becomes 17 over 17, which is 1. So t being 17 makes the exponent become a 1. And therefore, if I plug in 17, I get 700 times 2 to the first. So in other words, a of 17 is 700 times 2 to the first, which is 1400. And guess what? This means that 17 is the time it took for my investment to double from 700 to 1400. In other words, it will take 14 years in order for the investment to double. And this sort of jives with, if you think about our models from before, in the last problem about nitrogen, okay? This denominator, we got a denominator of 7 before. It took us 7 seconds for the radioactive nitrogen to halve itself. We're using the same concept here. It's taking us 17 years. It's taking us 17 years. Where are we? It's taking us 17 years for the money in the bank account to double. Whatever this base is saying, this bottom denominator of the exponent is saying this is how long it's going to take in order for this base to actually happen. And last but not least, we'd like the real life meaning of 759. Well, if you think about what we did, we got 700 to be 759 divided by 1.0416 squared. Okay? So if I look back up here, this is what I'm talking about. I'm talking about this green piece. 759 divided by 1.0416 squared was the 700. So if you think about what that is, if I were to multiply both sides of this equation by 1.0416 squared, it might reveal what's happening here. So I have 700 times 1.0416 squared gives me 759. In other words, if I think about what this is just really 700 times 1.0416 to the t when 759 means. My 759 is after 2 years, there will be $759, in the account. I hope this was helpful in explaining some of the manipulations that we're doing, and I'm hoping that you guys can kind of go and work through the rest of 5.5. Thanks.